In this video, I'm going to talk you through Topic 2 Electricity of the AQA GCSE Physics Specification. There are quite a few key terms that you need to be aware of when you look at electricity, and we'll start just by reviewing a few of those now. So the first one you need to be aware of is current. Current is a rate of flow of charge, so it's how many electrons pass a fixed point in a given period of time. Current is measured in amps, which has symbol A, and can be calculated using the equation where charge is equal to current multiplied by time. So just a reminder that current is the number of electrons passing a fixed point in a given time period, so how much charge is transferred in a given time. You could use the equation triangle which is over on this side of the screen to help your calculations. The next key term you need to be aware of is potential difference. Potential difference is the energy per unit charge, so how much energy is transferred by the electrons as they travel around the circuit. It's measured in volts and has symbol capital V. And it can be calculated using the equation that energy transferred is equal to charge multiplied by potential difference, or voltage. Again, I have included the equation triangle in case you want to use it over here. The final term you need to be aware of when we look at electricity is resistance. Resistance is anything that reduces an electric current within a circuit. It's measured in ohms and has symbol omega for ohms. And the greater the resistance, the lower the current. And the law that links those things is voltage equals current times resistance, and that's known as Ohm's law. Again, I've included the equation triangle for Ohm's law over here, and that's something that we'll look at in later slides. For your exam, you need to know the following circuit symbols, and we've got quite a range of them here. You also need to know what each of these circuit symbols does. So the first one is an open switch. When the switch is open, the circuit is broken and no electric current will flow. We've then got a closed switch. When the switch is closed, the electric current can flow around the circuit and the components will work. A cell is what provides potential difference for the circuit, and you need the potential difference to allow a circuit or a current to flow. Notice that the large side of the cell is positive and the small side is negative. A battery is two or more cells, so if you're ever asked to draw a battery, you must remember to include two or more cells to get a battery mark. A battery also provides a circuit with potential difference. We then have a diode. A diode only allows current to flow in one direction. So you can imagine if we had a current flowing, it's allowed to flow this way, but if we connect to the circuit the opposite way around, you wouldn't get a current flowing this way because the resistance is extremely high in that direction. Resistors are used to decrease the current usually if they're added in series, but also by adding resistors in parallel you can increase the current through the circuit. There are many different types of resistors. So this is a fixed resistor which can insert into the circuit, and that can have a fixed resistance and the resistance won't change. Whereas if you add a variable resistor, which has got the arrow going through it, then the resistance of that circuit can be changed by altering the variable resistor. The other resistors that we have are thermistors. They're heat dependent and they kind of have the hockey stick style that goes through them, and basically if you increase the temperature in a circuit with a thermistor, then the resistance of the thermistor will decrease as temperature increases. Obviously if you want to then cause an increase in resistance, you would decrease the temperature. So a temperature decrease will cause an increase in resistance for a thermistor. Light dependent resistors, or LDRs, they depend on light intensity. The greater the intensity of light, the lower the resistance, and therefore the lower intensity of light, the higher the resistance. LED stands for light emitting diode, and that's basically a diode that will emit light when the current flows through it in the forwards direction. We can now move on to the lamp, which is at the top over here. A lamp will just glow when current passes through it. You have a fuse as well. When a current passes through a fuse, the circuit's up and running, but if the current gets too high or you have a surging current, then the wire inside the fuse will melt and that will break the circuit. Voltmeters are used to measure potential difference, and they can be attached in parallel to the component you want to measure. And ammeters, they measure the current when that flows through them, and they should be connected in series. When we want to get an electric current flowing through a circuit, we need to have a source of potential difference. So for an electric charge to flow through a closed circuit, there must be a source of potential difference. We usually get that source of potential difference from a cell, a battery, or a power supply. Please remember that a battery is two or more cells. The potential difference provided by cells connected in series is the sum of the potential difference of each cell depending on which direction they are connected. Now the key thing about when you connect cells together, they have to be connected positive to negative. So you can see that we have the large side here. Remember I told you that already that's positive, and the small side on this side, that's connected to the large side, and that's connected to circuit. And we can see therefore that's connected correctly, and we will get an electric current flowing through there. The same would apply here because they're all connected in the same direction, but if we alternated that direction, then the potential differences of the cells would not add together. If we take each cell to have a value of 3 volts, we'd then be able to work out the combinations of these cells. So if these ones are 3 volts, then we've got 2 times 3 to get 6 volts for this one. Again, we've got 4 times 3 here, which would give us 12 volts. And in the final one, we've got 8 multiplied by 3, so we've got 8 cells, and that will give you 24 volts. We're going to look at the laws that govern current and potential difference in series and parallel circuits. We're going to start off with a series circuit. So a series circuit is a circuit where the current has only one direction to go in and there's no branches. So you can see if we look at the first one, you place your finger on here, you can go all the way around, there's nowhere else for it to go, all the current has to travel this way around. And the reason it would go that way around is that the current travels from positive, which is the large side, to the negative side there. You'll notice that the current is the same everywhere in a series circuit because there's nowhere else for it to go. And that's the first law you need to learn, is that the current is the same everywhere. So you've got 1 amp at this ammeter, which means if we place the ammeter here, we'd measure 1 amp as well, and here. And anywhere in that circuit, we'd always measure 1 amp. Notice that we place the ammeters in series, they go inside the circuit, and that's the way they should be connected if you have to draw them in the exam. If we look at a series circuit for a potential difference now, again, the current only has one direction to follow, it can only go this way around. The current cannot go through the voltmeter because the voltmeter's got extremely high resistance. But the voltmeters have to be connected in parallel so they go across the component you want to measure. The reason for this is so that the voltmeter can determine the difference in energy that the electron has before compared to after it goes through the component. So as the electron moves around this series circuit, as it enters the cell, it's given 6 volts worth of potential difference. It has that 6 volts that it must share between the components as it comes round. So it goes through the first one, which is the bulb in this case, and we'll give it 4 volts, and then it only has 2 volts left to pass on to the motor. And you'll notice that 4 add 2 give you the original 6 volts that it picked up from the cell. So the law governing potential difference in a series circuit is that the total potential difference of the supply is shared between the components. But please remember that no potential difference can be lost. It must all add up to the original it was given by a cell or power supply. As we move on to parallel circuits now, we can notice that the parallel circuit changes because when we get to this point here, so the current will come through the cell, comes to this point here, some of it can go this way and some of it will go this way. And it makes a branch, so that alternative pathways around the circuit that the electrons can travel. As a result, the 3 amps that comes through the cell, when it gets to this point, is going to split. 2 amps worth of electrons go this way, and the rest will go that way to make 1 amp. And they will recombine at this point here to make the original 3. So if you used to place an ammeter here, you'd measure 3 amps, an ammeter there would measure 2, and an ammeter there would measure 1. Now what you should notice is that 2 add 1 gives you the original 3 that you started with. So the law for current in a parallel circuit is that the total current through the whole circuit is the sum of the current through the separate branches. Looking at potential difference now, in a parallel circuit, we'll notice that the electrons will come through. They're going to go this way this time, because this is a positive side. They'll come through here. As they come through the cell, they're given 6 volts by the cell. As it comes to this point here, some of the electrons will come this way. Now, electrons that come this way only have one component to go through. They only go through the bulb. So they can give all 6 volts to the bulb and make their way back to the cell. In the same way, the electrons that come the long way around, again, they come through the cell, they pick up 6 volts. They come round this side, they go through a buzzer this time, but again, they're only passing through that one buzzer. So they can give all their potential difference to that one component, so they get 6 volts as well. Now I've added a final branch on here to my cell, and you'll notice that I've added this bit on here as well. So now the current through here would increase because we've got more options for it to go through at this point here. And what would happen is the current would come along here, and some of it will then go through this final branch. As it goes through that branch, there are 2 components, 2 bulbs, they will pass, and therefore potential difference will be shared between those 2 bulbs. Now if we assume those bulbs have both got the same potential difference, what we'd notice is that the 6 volts it gets from the power supply would have to be shared as well, and therefore we get 3 volts given to each of those bulbs. So the law governing potential difference in parallel circuits is that the potential difference across each branch is the same as that across the power supply. However, within a branch, the potential difference will split between the components like it does in a series circuit. Okay, so we're moving on to required practical activity 3 now. And the required practical activity 3 says use circuit diagrams to set up and check appropriate circuits to investigate the factors affecting the resistance of electric circuits. This should include the length of the wire at a constant temperature and combinations of resistors in series and parallel. On the screen you can see a circuit that could be used when carrying out this practical activity. That contains two cells, which is a battery, remember, an open switch, which can control whether the current is flowing through it or not, an ammeter to measure the current, the resistor we're going to measure, a voltmeter connected across the resistor, because that's the potential difference we want to measure, and then we've got a variable resistor, which will allow us to change the current. And therefore I could change the current and record the values of current over a range, and for each value of current I measure, I can measure the potential difference. I could calculate the resistance by using Ohm's law, which is V equals I times R, so R would equal potential difference divided by current, and then I would be able to work out the value of this resistor. If I wanted to change a circuit to test some of the other combinations that we need to do, so for example the length of a wire, or different combinations of resistors, I would just need to insert them into this part here. So I could take that R away, that resistor R away, and I can put in there a wire, for example, to measure the length of the wire and how resistance changes as I increase the length of the wire, for example. Or I could place into that part there a combination of resistors, which like the ones we're going to look at on a different slide. Things you need to consider when doing this practical is, number one, how you're going to determine resistance. And I've already mentioned that we would use Ohm's law, so potential difference is current times resistance, as shown here, or V equals I times R. And the other thing you need to be aware of is how you'll vary the current to get a range of values. There's two ways to vary currents in most circuits. You can either increase the power supply by adding more cells or taking cells away, or you can use a variable resistor to change the resistance of the circuit. And those are the two ways you can vary the current. When you vary the current, you need to measure the voltage or potential difference at those different values for current. So we're now going to look at what would happen if we use different combinations of resistors. So when you add resistors in series, the total resistance of the components added in series is the sum of the resistance of each component. So here I've got a 6 ohm resistor, a 3 ohm resistor, and a 1 ohm resistor. So the total resistance for the combination of resistors, which is shown here, is given by the equation that R total resistance, is R1 plus R2 plus R3 plus however many other resistors you've got. In this case, we've only got 3, so I can substitute in my numbers. So we've got 6 plus 3 plus 1, and therefore total resistance is 10 ohms. So those resistors added there have the same effect of just adding one 10 ohm resistor in a circuit. When I come to look at parallel combinations, the total resistance of the components added in parallel is smaller than resistance for the smallest individual resistor. And this is because electrons or charges have a different route to take, so the proportion of charge going through each resistor is lower. You are not expected to be able to calculate the resistance for combinations in parallel at GCSE. You could be asked how you would go about putting these combinations of resistors into a circuit. And as I said before, if you would go back to our original slide where we looked at this required practical, you would just need to, instead of putting in an R, you would just need to add this combination here, for example, into that one section, and you'd have a voltmeter across the whole thing. I'm going to look at required practical activity number 4, and required practical activity number 4 wants you to investigate the IV characteristics of a variety of circuit elements, in particular the filament lamp, a diode, and a resistor at constant temperature. Again, all of the circuit that you need to use here have been added onto the PowerPoint for you to see. So you can see we've got the two cells, which makes a battery, a variable resistor, ammeter and voltmeter, and that's standard for all the different circuits. The only difference really is that we swap this component. So for a resistor we include the resistor, for a bulb we include a bulb. The diode's slightly more tricky because we include the diode in the place of the other components, but we have to add a resistor in to protect the diode because diodes tend to have low resistance, and we also have to add a milliammeter to measure the current because they'll allow a lot smaller current to go through. In each case, again, just thinking back to the previous required practical we did, you need a way of varying the current. So to do that, you can add more cells, increase the power supply, or you can change the resistance. You'd only do one of those two things. In some cases, you might have to do variation to try and get a bigger range. The other thing you would then do is you record your current and your potential difference for each component, and you'd be able to put those onto a graph. And the main purpose of doing this activity is to try and look at what the graphs look like. As I mentioned before, the purpose of doing this practical was to get the graphs. So if you take the resistor graph first, if we plot current against potential difference, we notice that we get a line of best fit that goes directly through the origin and is straight, showing that current is directly proportional to potential difference at constant resistance. The reason for that is that a resistor obeys Ohm's law. We could say it's an ohmic conductor because it obeys Ohm's law, and that's why we get a straight line. If you were to work out the gradient of that line, then that would allow you to go on to calculate the resistance. In this case, the resistance would be 1 over the gradient, because remember, resistance is potential difference divided by current. If we look at a bulb, the bulb also obeys Ohm's law for a small area between here and here. But at higher potential differences or higher currents, we start to get this curving effect. And the reason for this is that for a filament bulb, resistance increases with temperature, which causes a decrease in the current. And remember that the temperature will increase as a greater current flows through, which is why we get the curving at the higher values of current. Whereas between these points here and there is still an ohmic conductor. Diodes have a very interesting graph. So because remember that a diode only allows current to flow in one direction because you've got a very high resistance in the backwards direction. So you get no current at all in the backwards direction. And then in the forwards direction, it would take a while for it to begin, but then you get a spike in current. And then again, that you can see increases in a linear rate. The key thing for a diode though is that current through a diode is in one direction only because it's got a very high resistance in the opposite direction. And also the graph for a diode will be the same as the graph for an LED, which is a light emitting diode, remember, and they'll have the same shape graphs as diodes. The only difference between a diode and an LED is that an LED will emit light when the current flows through it in the forwards direction, and you must be aware that LEDs use a much smaller current than other forms of lighting, which is why they're so efficient. We're now going to look at the difference between DC and AC. So DC stands for direct current, and in this case the current flows in one direction only. So this is the source of current that you get from your power supply or your cell or battery, and you can see here if you were to plot this as a graph, you'd have 0 in this direction in terms of volts, and you have a constant supply in the forwards direction in terms of your voltage being produced in a given time. You also need to be aware that alternating current is what's generated at power stations and travels through the national grid, and in that case the current changes direction 50 times every second. So alternating current means it alternates, and in the UK, because it's at a frequency of 50 Hz, the current changes directions 50 times every second. You should also be aware that the main supply has a potential difference of 230 volts. We can see this plotted on this oscilloscope trace here, so you can see it going up and down. Notice that the difference between the time here is 1/50th of a second, and your peak voltage will be 230. So we can now move on to look at power and fuses. Power is the rate of doing work, and the amount of power being used in an electrical circuit is given by power is voltage times current. So power is measured in watts, voltage is measured in volts, and current is measured in amps. You should also be able to link that to the equation that relates to energy and power, and the power rating of an appliance is simply how much energy it uses every second. And here we've got, so the power is the energy per unit time, where energy is measured in joules, power is in watts, and time is in seconds. We can use these things together now to derive one of the power equations. So one of the most difficult equations you have to learn is that power is equal to current squared times resistance. And one way that that's derived is if we use the equation for power is current times potential difference, which I've highlighted in red here. You should remember from Ohm's law that potential difference is current times resistance. So we can take the potential difference in this equation here, and rather than writing potential difference, we can write current times resistance. So again, power is current times potential difference, but rather than write potential difference, we can just write current times resistance, and you can see then that power is current multiplied by current multiplied by resistance, and that simplified down gives us power equals current squared times resistance. So now I'm going to look at 3-pin plugs. In the UK, all of our appliances are connected with a 3-pin plug. All countries will use an earth wire if the appliance is in a metal case, but our earth wire is built into our plug, which is one of the reasons why you need an adapter if you go to a different country. The earth wires work to make an appliance more safe if there's a fault in the appliance. So if there's a fault in the appliance which causes a live wire to touch the outer casing, the current surges, so you have an increase in current as it goes down the earth wire. This increase in current down the earth wire draws a much greater current than the fuse can handle, and so the fuse will melt and break. On this picture you can see an example of a 3-pin plug. We're just going to talk through a few of the features of it. So you'll notice the 3 pins represent 3 wires. The first one we're going to look at is the earth wire, which is green and yellow, and that goes to the top pin. The next wire is the live wire, which is where the current enters the plug, and that's brown. That is connected to the fuse, which is how you know which one's a live wire. The fuse, remember, will melt if the current goes above the certain value, which is the value of the fuse. So if you've got a 10 amp appliance, you would need to use a fuse that was slightly higher than the 10 amps, so you use a 13 amp fuse. You've then got the neutral wire, which is blue, which is where the current leaves the plug. All of those are surrounded by insulation to make sure it's nice and safe, so you won't electrocute yourself if you touch the wire, for example. And you have a cable grip to hold the outer insulation in place so it doesn't slide down and you don't get these wires exposed. You should be aware that the neutral wire of a plug stays at a potential close to 0 relative to the earth, and that's where the current leaves the plug. Whereas the live wire of the plug alternates between positive and negative potential difference at around 230 volts greater than or lower than the 0 volts of the earth. So how we get our electricity to our 3-pin plug is through the national grid. National grid basically is what connects the power stations to our homes and allows that electrical power to be transferred from the power stations directly to our homes. The voltage is altered before it goes onto the national grid, and it's altered by a step-up transformer. First of all, so the step-up transformer increases the potential difference but reduces the current. And the reason it reduces the current is because if there's less current, then there's less resistance. And if there's less resistance, there's less collisions between the electrons and the ions in the wire, and that means less heat is lost. You should be aware that power equals I times V, which is current times voltage. And so for a given power, you can change the current and change the voltage. So step-up transformers increase V and decrease I, again, to make sure that it's a more efficient process of transferring electricity to our homes. And the national grid is very, very efficient. Step-down transformers then are used to make sure the electricity is safe for our homes. So what they do is they decrease the potential difference by increasing the current, and that means that when the electricity comes into our homes, it's safe. This is just to let you know that the content on the slides after this slide will be for triple-only students. So if you're doing the combined pathway, you can stop watching now. But if you're doing the triple pathway, you can continue watching for the next few slides. So first slide for triple is static electricity. That's when certain insulating materials are rubbed against each other, they become electrically charged. So you can see if we have a cloth here and we rub it against this rod, they'll both become electrically charged. And the reason for that is that negatively charged electrons are rubbed off one material onto the other. The material that gains electrons, remember, because electrons are negative, will become negatively charged, and the material that loses electrons is left with an equal positive charge. So the fact that we've got positive charge on the rod and negative charge on the cloth means electrons have transferred from the rod to the cloth. You also need to be aware that when two electrically charged objects are brought together, they exert a force on each other, and that force depends on whether they've got the same charge or opposite charges. So two objects that carry the same type of charge will repel, as you can see here, two negatives repel, whereas two objects that carry different types of charges, so we've got negative and positive here, they will attract. The final thing you need to be aware of is that electrical charges can move easily through some substances, for example metals, and we call those conductors, whereas they will travel more difficultly or have more resistance in substances known as insulators. Examples of those are plastics. So we now move to our final slide about electric fields. A charged object creates an electric field around itself. The electric field is strongest close to the charged object, and the further away from the charged object, the weaker the field becomes. If a second charge was placed in the field, it would experience a force, and the force gets stronger as the distance between the two objects decreases. And the presence of an electric field is a reason for non-contact forces. The final thing you need to be aware of how to do is to draw field lines. So you can see that field lines occur for a proton and for an electron. So if you have a positive charge, the field lines are always pointing outwards, and they go all the way around. So these are the field lines here. Now the field lines are there to show the direction that a positive charge would move if placed at that point in the field. So you can see if we place a positive charge here, it would move away from the proton, whereas if we place a positive charge here, it would be attracted towards the electron. So the field lines represent the strength of the field by how close they are together, but also the direction that a positively charged particle would travel if placed in that field.